Hello class, this is CSE-4600, section 1, week 15, spring 2025. We're almost there. We're almost at the end. We just have one more project left to complete, and that is writing out a deadlock detection program. So, as we have done in the previous projects, we're gonna begin with a practice problem. And it is as follows. Here is the state of a system, and there is deadlock. Okay, we found deadlock, so what are we gonna do? Well, you're going to figure out which processes are deadlocked. So we have C, which is the currently allocated resources, R, which is the requests for resources, E, which denotes how many resources are currently in existence in the entire system, allocated or not, and A, that's just the number of each resource that is yet to be allocated to any process, or rather, the amounts of each resources that is available in the system. So this system state is deadlocked. Your goal is to figure out which processes are deadlocked. Yeah, and that's it. You're gonna confirm that this is deadlocked, but you're also gonna check which processes are deadlocked. So, again, this is deadlock detection. In a system, there are going to be processes, and some of them might be deadlocked, some of them might not be deadlocked. There might be several instances of unrelated deadlock, or there might be one big deadlock. Our goal is to figure out which processes are deadlocked and which ones are not. So once we solve this program by hand, once we solve this problem by hand, we're gonna write a program that's gonna solve it for us. To do that, we can begin with the sample code here. It defines several functions here. Well, yeah, we're gonna define several functions here. Even though we only have one deadlock detection algorithm, we have a few helper functions because some of the code is repeated, and we just want the helper functions to help out, to make it easier to write out the code. There are also a few type defs, so the type defs aren't necessary, but I've added them anyway for ease of understanding. Because there are two main data structures we are working with our deadlock detection algorithm. The first one is a vector of resources represented as a vector of ints. The other one is a matrix representing, that is the data type of two of our data structures here, C and R. So again, C is the currently allocated resources, R is the current requests for resources. In code, we need that to be a vector of ints because it's a little bit clunky to write vector int. We're just gonna make a type def and alias that to be resource matrix. Like how we can alias vector int to be our resource vector. If you've never tried to work with type defs before, I recommend you start learning now, because when it comes to writing code that is self-documenting, type defs are probably a good way to write code that is easy to read. Anyway, you actually need a third data structure, and that is a vector of bools. Because in our deadlock detection algorithm, we are marking processes as terminated or not terminated, and the vector of bools that we alias to bitmap, it's a bitmap that denotes which processes are terminated or not. So again, we need three helper functions for our main deadlock detection algorithm. Once we write our function prototypes up here, we can then proceed to our main function. So the code here represents the state of a system from our PowerPoint slides. So we have E, A, C, and R. Turns out we don't need E at all, since we can infer what E is supposed to be by doing some math. If you recall, if we sum the columns of C and then add them to the corresponding values of A, we get the values of E. So, in other words, we only need 3 of the 4 data structures shown here. We don't need E, but we do need A, C, and R. And again, these 3 data structures represent the current state of a system, and we want to determine whether it's deadlocked or not. So this state is actually not deadlocked at all. So when we build this algorithm, once we run it, we're gonna get an output that says it's not deadlocked at all. The 3 helper functions are pretty small. Although I give you the function definitions, it's up to you to fill in the necessary blanks here. So the first one is the less than function. We define a vector v1 to be less than vector v2 if the corresponding values, if each value in v1 is less than the corresponding value in v2. Though technically it should be less than or equal to. So we define our less than function here. It's just a matter of filling in the blank. So that is part 2a. Part 2b is we're gonna check whether all of our processes have terminated. And we pass into this function our bitmap that represents processes that have been marked as terminated or not. If all processes are terminated, that means every bool in the vector is true. If any one bool is false, that means not all processes have been marked as terminated. So this helper function is here to check whether every process has been marked as terminated or not. The third helper function, that's just there to print out one of the vectors in our program. And we are going to print out some of the vectors that in this program. So because that's going to be repeated code, I've made it into a helper function here. So part 3 is the entire deadlock detection function itself. We need to define 4 variables and data structures. The first 2 is the number of resources and processes in the system. The next one is a copy of A here. So we pass in the currently allocated resources, the current requests, the currently available resources, the currently allocated resources, and the current requests in the system. Because we're passing them in, and it's good practice to have these parameters be immutable, that is, they cannot be changed. And because of that, we want to make a copy of A here. So that's what this is here. We also need to make a bitmap of bools because, again, we need a data structure that represents which processes have been marked as terminated and which ones are not. And then we can proceed with writing an entire while loop. And I do have the code skeleton here, and it's a matter of filling in the blanks. But I have it written up here, and the code is as follows. We're going to repeat this following code until we break out of the loop in one of 2 places. So the first thing we do is check whether every process has been marked as terminated. If so, we break out of the loop, and if not, we continue to the next step. here we define a variable called process index that holds the index of a process. We're going to set that to -1 because the next step is to iterate through the entire matrix of requests. For each row, we're going to check whether the corresponding process was already marked as terminated. If so, skip to the next row. If not, proceed to the next step. And that step is to check whether the row is less than or equal to the available resources vector. If so, store the index of the current row in process index. If not, skip to the next row. So we iterate through the entire matrix of resource requests. And what we're doing is finding one request that can be satisfied. So one of two things is going to happen here. Either we find a request that can be satisfied, or we find that no such request can be satisfied. If we do find a request that can be satisfied, that means process index is going to be some number other than -1. Well, more specifically, it's going to be some non-negative number. Non-negative number or 0. If so, that means we found a satisfiable request. That means we can do these next steps. Take the row corresponding to the process's currently allocated resources and add it to the vector of available resources. Then we mark the process as terminated. And what we want to do is print out the process that has been marked as terminated. Because again, when we have a system with resources, some processes are going to deadlock while others can continue to completion. The unrelated processes have nothing to do with the deadlock, unless they stole resources. But, again, we need to mark which processes can run to completion, even if there are processes that cannot. If we found no such satisfiable request, it means there are deadlock processes. So we iterate through the iterate through the matrix of requests, find a request that we can satisfy. If we can't find such a request, and we've determined that there are still some unmarked processes, that means we have deadlock. At that point, we're going to print out that deadlock has been detected, print out the processes that have not been marked as terminated, therefore those processes are deadlocked, and then we're going to print out the state of the algorithm that consists of the currently available resources and each deadlock process's currently allocated resources and requests. And then we're going to break out of the loop. Because once we've detected that there is deadlock, or alternatively, once we've detected that every process can run to completion and therefore is not deadlocked, we're going to break out of the loop. And again, the code is here, and it is an infinite loop where we break out of it in one of two places. So, check whether all processes have terminated. If so, break out of the loop. Iterate through each request, finding one that can be satisfied. Skip requests for processes that have been marked as terminated. Check whether the process is marked as terminated. If so, continue. That means we're going to skip to the next row. Check whether the request vector is less than or equal to the available resource vector. If so, save the index of the found process. If not, continue to the next row. After the loop, check whether a request has been found. If so, add the process's currently allocated resources back to the copy of A, then mark that process as terminated. If not, that means there are processes that are deadlocked. So these are the steps you have to do if we have found a request that can be satisfied. Otherwise, these are the steps that we do if we find no satisfiable request and determine that there is deadlock. And that's it. Once you've written the entire definition for the deadlock detection function, we're gonna modify our program so it calls the deadlock, pass in available, current, and requested, and it's going to print out a message that says, hey, we found deadlock, or no deadlock exists in the system. After that, we're going to do some experimentation. So it's as follows. Of course, we're going to confirm that the results we got in part 0 are correct. So this represents a state, the state of a system that has deadlock. We're going to confirm that we do have deadlock. Actually, more specifically, we are double checking the result that we had made from doing this problem by hand. The next thing you're going to do is we're actually going to change the state of the system by making more resources available. So the available resources are 0, 1, 0, 2, 1. We're going to change those values until we don't have deadlock anymore. So how many resources must be available until we don't get deadlock? I'll give you a hint right now. You only need to change one value. You could also just make every value in A to be a large number, like make every value to be 100, and no deadlock would happen because there's so many resources available that every process request can just be satisfied right then and there. But pretend that adding new resources is expensive, so you want to add as little resources as possible. So that's the second thing that you're going to experiment with. The third thing you're going to experiment with, which is actually two things, you're going to come up with a new system state that is deadlock, with at least 3 processes and at least 4 resource types. And then you're going to modify it by changing the values of A so it isn't deadlocked. So you're going to come up with your own C, R, and A, one representing a deadlocked state and the other representing another state that isn't deadlocked. Once you created a deadlocked state, you're going to change it a little bit so it isn't deadlocked. So yeah, you're going to repeat doing this problem, except you're going to enter your own state. You're going to enter your own values. You could just use the same thing as before, and then just tweak the values. But once you've gotten a deadlocked state, you need to change it. You need to change the values in A so it isn't deadlocked anymore. Again, don't just change all the values to A to be like 100. We want to add as little resources as possible so that it doesn't result in deadlock. And that is it. So those are the instructions you need to do to complete your deadlock detection project here. So the rest of the video is going to be a more detailed how-to for the project. So if you feel like you got a good handle on what to do with this project, if you feel like you're confident in your ability to write out the entire program without any further assistance, then I say go for it. Otherwise, if you would like some assistance, then stay here and enjoy the rest of the video. Okay. First thing I'm going to do is I'm going to create a... That's the trash. I don't want to go there. I need to create a brand new text file. And I'm going to save this as... Let's go back and find our 4600 project file, go to project 3, and I'm going to name this project 3.cpp. Oh, by the way, we are working with C++ because we're going to be working with the data structures that C++ has available to us. So, here is our project 3.cpp file. We're going to begin by populating it with the boilerplate code first. So, IOStream for cout, include vector, and include string. I'm not sure if string is necessary, but we're just going to include it just in case. Okay. Now, we need to add our function prototypes. Okay, my bad. We did not need to include string at all here. So we're going to proceed with the rest of our boilerplate code, which is where we need to define our function prototype. So oh yeah, probably also a good idea to include our type defs as well. Again, this is just for ease of programming. We could just write it out as standard vector int address v1, and then just copy this whole thing and call that v2. This works too. The reason for the type defs is, again, for ease of understanding. So I'll include the type defs here as well. Type def standard vector int resource vector, and then type def standard vector standard vector int. And again, these type defs are just for ease of programming. We're just aliasing this so that this, we can just write this in place of this. Let's write the rest of our function prototypes. Oh, by the way, I am passing it by reference rather than by value, because that way it's less stuff being moved around. And I'm adding the const keyword because we don't want our function being called to make any changes to our vector. So the const keyword is there to keep our vector from being modified, and we're passing it by reference because that's just less stuff being passed in. We're only passing in the address rather than an entire copy of the vector here. Which is probably something you will have learned, hopefully in one of the lower level classes, probably the 2000s level courses. Okay, let's add that print function. You know, I'll just use the type def because it's basically the same thing as typing in standard vector int. Right, and now we just need the detect deadlock function prototype. And I just went ahead and used the type test because, again, it's, at least for me, it was just easier to understand that way. Okay, now we can write our main function. We're just gonna hard code our 3 data structures. So although I won't talk about it in depth here, I do talk about it in the previous projects where we can just set up the program to accept user input. I'm not going to do it here just for the ease of getting the instructions out, but it is something that is probably worth doing. Probably better if you can have it read the system state from a file. That's what what include string was for. That was for a attempt to read the system state from a file. But I'm just gonna hard code it here. We could go above and beyond and add a means of accepting user input or reading from a file. That way the program can work with any system state, not just the one that we hard code. But I'm just gonna hard code it just for ease of demonstration. And again, this is for a state that is, okay, this is for a system state that was described in the PowerPoint slides. So this looks like a nested array. It kind of is. But yeah. Let me just write the rest of it. And I'm gonna make a copy of this, paste it down here, and I'm gonna have that be my requested resources. But I need to change the values here. So 2, 0, 0, 1, 1, 0, 1, 0. And 2, 1, 0, 0. And then we're gonna call detect deadlock, pass in available, current, and requested. And that's the end of the program. But we're not done yet. We need to define all of our functions up here. So let's do that. So the 3 helper functions are pretty simple to define. Let's do that real quick. What I'm going to do is I'm just going to copy these 3, paste them down here. So these are our 3 function definitions. I'm just going to define our less than function as follows. I'm going to define a bool up here. It's less than equals true, and remember our definition for a vector being less than another vector. That means for each element I in each vector, the ith element of the first vector is less than or equal to the ith element of the second vector, and that holds true for every I. How do we determine that? Well, we can just check each element one by one, and we do that by just writing a for loop. I is less than 0. I is less than. How large are these vectors? So we can determine the length of a vector by, okay, assuming that these 2 vectors are the same size, let's just say v1.size. So that is a member function that returns the number of elements in the vector. And then I++. Now, there's several ways we can write this. We can just write it as is less than equals is less than Boolean and then v1 I is less than or equal to v2 I. Yeah, there's several ways we can write this. That's just the long way. The short way is to replace that with is less than ampersand equals v1 is less than or equal to v2. And once we have that, we can just return is less than. Our next function, all processes terminated. How do you determine whether every process has been terminated? We're gonna check whether every single bool in the vector is true. And once again, we're gonna use a for loop for that. So what I'm gonna do is cheat. I'm just gonna copy the code from the previous helper function, replace some names, all terminated. There we go. And we have our bitmap of processes. We don't have v1 or v2 anymore, so I need to replace that with for int I equals 0, I is less than processes.size, I++, all terminated, ampersand equals processes, square bracket I. Because we're ending all of those bools together, and it's going to be true or false. We're going to add a redundant true at the beginning because we need this all terminated value here to be returned. So we're going to start with the redundant true, then we're going to AND it with all of the bools in our bitmap. Remember, the bitmap is for, we use a bitmap in our algorithm to determine, to mark off processes that are marked as terminated or not. And that print resource vector, well, I'm gonna cheat again and just copy paste the code here. So here's what's going on. We need to print out every element in our vector. And to do that, we need yet another for loop. So I'm just gonna copy this. Because there's no vector called processes, I'll just replace it with v. And we need to print out each element in the vector. So we can just use cout. So of course we need to add a space. And that's it. No end line, because I want to have all of these values to be on the same line. Alright, there we go. Now we have our 3 helper functions complete. They're all pretty simple. Oh yeah, I had made an error in the function prototype here. So print resource vector, that's a void function. Therefore, this should also be a void function. I guess to be clear, our deadlock function should also return a bool. And then we can use that to print out, and then we can use that to do some other logics, such as printing out the results to a file. So if the current state is deadlock, we're gonna write the result to a file. I have it as a void function because it's just gonna say whether or not it is deadlocked, but we don't really use that information much else. So let's copy these 3 lines here and paste that at the bottom. We're now ready to write the entire deadlock detection algorithm. How many resources are there? Well, resource vector A, the length of that is how many resources there are. So I could just write in something like A.size. And that's it. That's our number of resources. Next, we need int num processes. How do we get that? Well, hold on. My bad. I had made a mistake in here. So this should be resource matrix. So there's one resource vector and then two resource matrices. So I need to change that prototype up here so it's resource matrix. There we go. How do we determine how many processes there are? Well, resource matrix is a vector of vectors. That's just how large the outer vector is. So we can just define that to be C.size. Because C is a vector of vectors, C.size gives us how large the outer vector is, and then C square bracket I dot size gives us the size of one of the inner vectors. Right, so now we have the number of resources and number of processes, and we need those for our for loops that we're going to perform. But before we do that, we need to declare a bitmap. So there's a bitmap, and every bit in the bitmap is initially going to be false. So there's several ways we can do this, and one way is to just create a for loop that fills the entire bitmap with falses. And that is one way to do it. There is another way where we could just do it as one line, by the way. I'm just going to show it as a for loop, just for ease of understanding. Again, there are other ways to do this. Finally, we need to make a copy of A here, because we need to change the value of A, but this is passed by reference and is immutable, so we need to make a copy of it. So and for that, we're just going to make another for loop. For int I equals 0, I is less than num resources. Because vector A represents the number of each resource that is available in the system. But we want to make a copy of it, so let's just do this. A copy dot push back equals A dot copy pushback dot pushback, and then parentheses A square bracket I. There we go. And now we're ready to write that entire for loop. Okay, now let's begin writing that while loop. So this is an infinite while loop. It's going to repeat and repeat until we break out of it. So first you need to check whether every process has been marked as terminated. And we already have the function here that returns all process, that determines true or false based on whether every process has terminated. So all we gotta do is all processes terminated, and we just have to pass in the bitmap up here is terminated. If so, what we're gonna do is we're gonna print out a message. verify that there's no deadlock, and then break. There we go. And then break. Because if we don't break, we're gonna get stuck in the loop. Next. Find a request that can be satisfied. Find a process's request that can be satisfied. Skip processes that have been marked as terminated, by the way. So, int we need that process index to keep track of which process has a request that can be satisfied. And then we're going to use a for loop to iterate through the entire matrix of requests. I is less than. Okay. Check whether the current process is marked as terminated. If so, continue. And we're going to do that by looking at our, oh, not that one, is terminated. So, is terminated, I equals true. Though, if true equals true, that's already true, so we can just reduce it to just is terminated. But we need to have that be as part of an if statement. If is terminated, then continue. There you go. Next. Check whether request is less than or equal to available resources. If not, continue. So basically we're going to find a process whose request can be fulfilled. So what we're going to do is this. If, and we already have our less than function here. So if less than, what is our process's request? So that's going to be a row vector from resource matrix R. So we can just pass in R square bracket I. That represents our current process's request for resources. And then we're going to compare it to a copy, because we made a copy of A. There we go. If if Ri is less than a copy, that means process I's request can be fulfilled. That means we can then change the value of process index to be I. And then what we can also do is break out of this for loop, so that way, once you find a request, we don't have to look at the other requests anymore. If there is another fulfillable request after that, we're gonna address it after that. By the way, if we go through the entire matrix of requests and find more than one eligible process, it doesn't matter which one we pick. We just gotta pick one, and we're gonna pick the first one. Okay? Okay. Okay, but we're not done yet. Really what I To make sure that this works as expected, let's put this else. Continue. That way, if the process has already been marked as terminated, but the current request cannot be fulfilled, we're just going to continue to the next for loop iteration. We're going to check the next row after. Okay, now we are done with the for loop, and we're going to see whether we have found a fulfillable request. If we had found a satisfiable request, we're going to mark the corresponding process as terminated, and then we're going to make its allocated resources available. If, on the off chance, that request was the last request in the matrix, it's not going to falsely flag the whole thing as deadlocked, because we found a request. That means this process index is going to be some number other than -1, some non-negative number that is not -1. So, because we found a process whose request can be fulfilled, the next time that this for loop runs again, it's gonna check whether every process has terminated, but once we fulfilled that last request, every request has been fulfilled, every process has marked as terminated, so the next time this while loop runs, it's gonna break. Okay, so let's do this. If the process index is less than or equal to 0, that means we found a process whose request can be fulfilled. Else, that means we have deadlocked processes in our system. Let's focus on we found a request that we can satisfy. So, add back allocated resources to available resources. And then mark process as terminated. Let's fill in the code. So how do we add back those resources? Well, the corresponding row in A represents the resources. No, not A. A is the available resources. So we're going to add onto A the corresponding row in C. And that's basically vector addition. That means we have to do a for loop where we add the corresponding elements together. So we can just write it as follows. For int I equals 0, I is less than num resources I plus plus. A copy plus equals, and we're gonna go up here. It is the corresponding row in C. So C square bracket I. There we go. So yeah, add back the allocated resources to the available resources. And then mark the process as terminated. So, press to mark that process as terminated. We're gonna access the bitmap. No, not that one. The bitmap here is terminated, process index equals true. And then we're going to print out that process. So standard cout process process index marked as terminated. There we go. Next thing we have to do is consider the case where we found no such process whose request can be fulfilled. So, if that is the case, if we go through the entire matrix of requests and find no requests that can be satisfied, and there are still unmarked processes, that means those processes are deadlocked. So the first thing you can do is say that we've detected deadlock. And then we're going to print out which processes have been deadlocked. And how do we print out each process that has been deadlocked? Well, we're going to iterate through our bitmap, and for each process that has not been marked as terminated, we're gonna print out that process is index. If not is terminated I, we're going to print out process I. And there we go. So process I is deadlocked. We also want to print out the processes currently allocated resources and current resource request. So it means we need a copy of this for loop. And we're going to replace the print here with, we're going to print out each process's current request for resources and currently allocated resources. And we have a print function already made called print resource vector. So let's just copy that and we'll paste it here. And what we're gonna do first is standard cout process I. This is allocated resources. Or I could write it a different way. Allocated resources of process I. And there we go. And then print resource vector. So what is the allocated resource of that process? It is going to be the corresponding row of one of our two matrices. So allocated resource is going to be one of the rows in C. So C square bracket I. There we go. We also want to print out the request for resources, so I'll just duplicate those same two lines. Request of process I, print resource vector, and that's going to be a corresponding row in R. Okay, so that is the whole program. And now, let's see if this whole thing works. It's only one algorithm, by the way, but it did take quite a few steps to get it to work. No, not GCC. Because this is C++ code, we want G++, -O, project 3, project 3.cpp. Press enter. Okay, okay, there are a few errors here, and they all stem to either is terminated or our bitmap. So, the issue was, I forgot to type that for our bitmap. So, let me just copy that, place it down here, type depth standard vector bool bitmap. There we go. So let's try that again. Clear, recompile. Okay, wait, detect deadlock. Line 130 looks like I'm doing something wrong. And yes, the problem is I'm adding a value to a vector, which doesn't make sense. What I need to do is add a value to another value in that vector. So it should be a copy and then square bracket I. Because this is supposed to be vector addition. Alright, let's clear that and see if it... Did I save this? Double check. Clear. Okay, Okay. The issue is I'm trying to add a vector to... It's not that I was trying to add a value to a vector. Rather, I'm trying to add a vector to a value, which doesn't make sense. So, it should be C square bracket process index, because C is a vector of vectors. We want to access one of the inner vectors and then access one of the elements within that vector. So it should be C process index in square brackets and then I in square brackets. Let's try this again. There we go, it worked. Now / project 3, press enter. Process 2 marked as terminated, process 1 marked as terminated, process 0 marked as terminated, no deadlock detected. Which follows what we had done in class, where we stepped through our deadlock detection algorithm and determined no deadlock exists. Now, let's go ahead and have a little bit of fun. From the same set of slides, we changed one value in R, and that made the whole state deadlocked. So let's do that. So in our request matrix, we're going to change the last value from 0 to 1. That means the last process also needs a Blu-ray drive that we don't have. So let's recompile our program and run it. Oh no, it's looping! And I think I know why. It means somewhere in this code, I forgot to add a break. There we go. Let's recompile that and rerun it. Okay, so there is one slight error in how the vectors are being printed out. I should have a end line over here. So standard, cout, standard, end line. I'll just copy that and put it down here. And that's because the print resource vector helper function, at least how I've written it out, there is no end line on the line that's being formed. So let's clear, recompile, project 3. Okay. Okay, but I want to add some spacing to that. And again, this is just for clarity. So this for loop prints out each process, but I want to add an extra end line after that. And then after this, I want to add another end line. There we go. Let's recompile and look at it again. There we go. Now the output has proper spacing. So that way the resources of process 0 and the requests of process 0, they're all grouped together. Deadlock detected, the following processes are deadlocked. Processes 0, 1, and 2. Allocated resources of process 0, request of process 0, allocated request. There we go. It's showing that every process has been deadlocked. Okay, but let's have even more fun. What if we had another process that will run and not get deadlocked? So we know we have resources available 2100. What if we added another process that has no resources allocated to it yet? 0000, but it's requesting 1100. Can we fulfill this request? Is this row less than this vector? I'll tell you right now that it is, but let's test that out. Okay, I think that's because I forgot a comma somewhere. There we go. Clear. Recompile. And run. So one process can run to completion, but the others are deadlocked. So 3 processes are deadlocked, but the one that we added does not deadlock because whatever resources we had available, those are resources that we already have. Let's do this. Let's add an extra Blu-ray drive to the system, and then run this program again. No deadlock detected. So what I did was a hint of what you're to do in the last part of your project here, which is to come up with another deadlock state, and then modify it so it doesn't become deadlocked. So yeah, come up with a new system state that is deadlocked with at least 3 processes and at least 4 resource types. Then modify the state by changing the available resources so it isn't deadlocked. So do it so that you don't make the available resources some large number. Rather, just tweak the values as little as possible until you get a state that is no longer deadlocked. So let's do this again. We could just go ahead with this example here, but ideally I'd like for you to come up with your own example. If we have this state here and run it, so this is a system state. If we run a program, it's deadlocked. One process terminates, but the others do not because they're deadlocked. But by changing it so we have one new resource available, once you compile it, suddenly every process can now run to completion, therefore no deadlock. So yeah, that's the gist of your entire project. Of course, you also have to enter this into your program to see what processes are deadlocked. So I'm going to leave that as an exercise for you, because again, that is something that you're going to have to try on your own. But yeah, that is the gist of the entire project. Alright, so if you have any questions, definitely let me know. But yeah, once this is done, that's gonna be it for the entire class. So, yeah, we're at the end. Alright, so that's gonna be it. Hopefully I'll get to see you again another time, perhaps in another class, but until again,